Friends, welcome to the lecture number 28 on module 1. We are going to discuss about 3D truss analysis in this lecture. We will extend the same logic what we had for 2D analysis of truss members and make the analysis as simple as that to understand 3D analysis concepts. Of course, whatever we learned in the analysis of 3D space frames will be also used in 3D analysis concept of truss members. Generally, we are having some valid assumptions what we made in the 2D analysis of truss structures, that is joints are assumed to be pinned joints, pinned connections, which is one of the basic assumption what we made in analysis of planar frames. Is also valid for 3D truss system. More interestingly, we have developed a beam element is it not? We have developed a beam element. We will use that element with a small modification. We say that the beam element has spherical hinges at both the ends. What is the consequence of this assumption? The consequence of the assumption is it can freely rotate about any axis. Okay, that is the consequence. So, the end rotations will be actually 0. Okay. Therefore, what would be the degrees of freedom now we have? Earlier for a beam element, if we look carefully, we had 12 by 12 matrix, that is each end had 6 degrees of freedom, 3 translations, is it not, along x, along y and along z, and 3 rotations about x, about y and about z. We had 6. Since we have made spherical hinges at both the ends, the degrees of freedom now are restrained with 3 displacement components in each end of the member. And most important fact, truss members can resist only axial deformation and axial forces. So, no moments. So, that makes the stiffness matrix of the member as order 6 by 6. Let us draw a typical truss member arbitrarily oriented with hinges at both the ends. So, one is local, other is global. I call this as a reference axis system. For the local axis, let us mark the axis as x m anti-clockwise direction, we know it is ym, and we have zm marked here for the member whose j and k ends are marked and the member is I. Okay. So, let us have 3 axes in all the places. Okay. Let us now mark the global axis of the system. Let us say this is my x, y axis, and let us say z axis. Similarly, all the 3 axes at this joint. Okay. Let us now mark the degrees of freedom. Let us say along xm, I call this as displacement t and this as displacement r, okay, and this as displacement v. We are using the same notation. If you carefully look at the notations of 2D planar truss analysis, except for z axis displacements, all notations are same. Okay. Similarly, this will be called delta h, this is delta t, sorry, delta s, and this as delta w, which is same as the beam element what we used in the earlier derivation. Okay. So, let us also mark the corresponding forces for our understanding. Axial forces, I can call this as P t, this as P r, this as P v, this as P s, this as P h, and this as P w. Let us now correspondingly mark the global displacement degrees of freedom. We call this as delta t bar, this is going to be delta r bar, and this is delta v bar, and as simple as that delta h bar, delta s bar, and delta w bar. Let us also mark the corresponding forces. So, P t bar, P v bar, P r bar, P h bar, P w bar, and P s bar. So, P indicates axial forces in respect to degrees of freedom at j and k ends, and the degrees of freedom are marked which are similar to exactly the beam element, except that the ends of the members are spherical hinges which can rotate about any axis freely. Therefore, there are no moments about any of these 3 axes. So, obviously, we realize that the stiffness matrix will have a size 6 by 6. So, now let us say I want to connect my displacement or the forces P t, P r, P v, that is at the jth end, P h, P s, and P w. This is displacement, this is displacement, sorry, forces at jth end along x, y, and z, and this is forces at kth end along x, y, and z, which will be equal to the stiffness matrix connecting these displacements delta t, delta r, delta v, delta h, delta s, delta w. So, these are displacements at jth end at x, y, and z. These are displacements at kth end at x, y, and z. Connecting will be a stiffness matrix. This is 6 by 1, this is 6 by 1. So, this has got to be 6 by 6. The labels could be T, R, V, okay, H, S, and W. So, this will be at jth end displacements, is it not? And this will be at kth end displacements along x, y and z, along x, y and z. So, obviously, for a truss member, you know, this value will be k t t and r and v contribution will be 0. Then you will have k h t and these two will be 0. Similarly, for the column h, you will have k t h, this will be 0 and k h h, this will be 0. Remaining all members for a truss element will be 0 in this stiffness matrix. Okay. So, that is my stiffness matrix. I can now say the force local of the truss member of ith member is given by stiffness matrix of the truss member of the ith member multiplied by the displacement local of the truss member of the ith member, only equation number 1. Okay. Now, I want to find the forces, okay, which will connect the global forces. So, let us say P at jth end along x, P at jth end along y, P at the jth end along z. Similarly, P at the kth end along x, P kth end along y, P at the kth end along z, which will be now connected by some matrix which will connect the local to the global. So, P bar j x, P bar j y, P bar j z, P bar k x, P bar k y and P bar k z. Okay. So, now this is again 6 by 1, this is 6 by 1, this has got to be 6 by 6, but interestingly I can now divide this at 4 quarters. So, this will be C 1 1, C 1 2, C 1 3, 2 1, 2 2, 2 3, 3 1, 3 2 and 3 3. Remaining this particular part will be 0 and by symmetry this will also be 0 and this will repeat as 1 1, 1 2 1 3, 2 1, 2 2 2 3, 3 1, 3 2 and 3 3, which is the order of same style as that of beam element in a 3D analysis, except that in a beam element it was 12 by 12, but in a truss element it is 6 by 6. So, now I can write now this as P of the truss element local will be given by T of the truss element transpose matrix of I and by connecting of the truss element ith member, equation number 2. I can also expand this matrix as T of the truss member of every member, simply can be said as C T I 0 0 and C T of the ith member, is it not? So, now with this algorithm we can always say the displacement of the truss member simply is T of the truss member with displacement bar of the ith member. K transpose of the truss member can be also said as T transpose, this is K bar, this is K bar of the truss member is T transpose K of the truss member with the T of the truss member. This is for every member. So, I can call this equation number 3 4. Okay. Further, we can always say the forces in the ith member is K multiplied by the displacement of the ith member plus any joint load applied on the ith member, equation 5. If we want to find the forces in the global degrees of freedom, this can be simply said as K bar of the truss member of the ith member multiplied by displacements of the truss member in the global degrees of freedom plus transformation of the loads in the global degrees of freedom. So, friends, very interestingly, for a truss member which is arbitrarily oriented in space, one can either use YZX transformation or ZYX transformation So, therefore, all equations for YZX transformation and ZYX transformations which we derived are applicable as it is without any change, no change is required, straight away we can apply. So, using YZX will enable you to compute the psi y angle, using ZYX will enable you to compute the psi z angle. So, the equations derived for 3D beam element for obtaining the psi angle is for truss members also. There is only one important catch. If truss members are loaded only at their joints, which is usually a common phenomena. Only joint loads are considered, okay? No member loads. So, usually a common phenomena. In that case, orientation of the local axis of the member with respect to the reference axis of the system is not important. That is a very great relaxation we have. That is a very great relaxation we have. We do not have to bother about the orientation of the local axis with the global axis, provided if the loads are only applied at the joints. In that case, the xm ym axis can be positioned so that the psi angle is practically 0. So, if you agree upon this statement, then Cy, which was derived earlier, can be now modified for the truss member very easily by taking psi angle as 0. So, Cy is given by Cx, Cy, Cz minus Cx Cy by root of Cx square plus Cz square, root of Cx square Cz square minus Cy Cz by root of Cx square Cz square minus Cz by root of Cx square Cz square 0, Cx by root of Cx square Cz square, that is Cy. You can also write Cz for ZYX transformation as Cx, Cy, Cz. We derived this equation earlier, except that we are substituting psi angle as 0 in the whole equation. Okay. Minus Cy by Cx square plus Cy square, Cx by Cx square, Cy square 0 minus Cx Cz by Cx square, Cy square minus Cy Cz by Cx square, Cy square root of C x square plus Cy square. So, friends, we can make use of the existing derivations and try to solve a simple 3D truss problem. So, we have learnt how a 3D truss analysis is different from 3D space frame analysis. In the problem formulation, we have assumed that ends are containing spherical hinges, that is the first assumption we made. Second is, if loads are applied at the nodes, that is at the joints, we do not have to bother about the psi angle, keep this as 0, directly do the transformation matrix. So, its analysis is simpler. I believe that you will be able to understand and use the same program with a small modification of a 3D element and solve a truss problem and try to understand the application of this programming for the truss problem easily. So, friends, we will have another one more lecture in module 1, where we are going to talk about the special elements, that is non-prismatic members, how they can be handled using what is called as substructure technique, which we will discuss in the successive lectures. Thank you very much and bye.